go ahead.
So we're the Disney project, also known as the Roller Coaster Torch Stripe Inspection AI. I'm Brenda, that's Corey, and that's Ricardo. So first we're starting off with the planning, so basically the problem and how we found a solution for it. So the problem is, Disney's, this is what they proposed to us. Their problem is that due to constant vibrations of roller coasters, bolts tend to get loose because of all the vibrations and the friction and everything. So they need to always inspect it. So first they started off with torque stripes. So torque stripes is an actual visual indicator, so it's just a line. And if it's unaligned, you know if it's loose, and if it's straight, you know it's still good. But that you still have to check every single bolt. Sure, you don't have to actually physically move it. You can just look at it, but you still have to check every bolt. So the plan was that they wanted us to create an image detecting AI that can just look at a torque stripe and be like, okay, it's misaligned, therefore it is loose, or it's still straight, so it's still good. So Disney preferably didn't really care. They could be a video with the bolts, or it could be real time. We decided to do both, just to make it easier, and also real time was more of a hardware element that we could add. Other requests were also to indicate a location of the bolts. And so we realized that for the requirements for software, we need to identify a bolt, identify the torque stripe, identify the condition of the torque stripe, whether it's misaligned or not, identify the location of a bolt, and then for hardware, it's having the AI detect through either real-time and video processing.
All right, for creating the AI, this is what we had to do. We use a TensorFlow library because that's what the previous Disney group that worked on this used. TensorFlow is a neural network as well. It's Google's neural network, and it helps build the computer learning and whatever you feed it. We also use Keras, which is also a neural network, which builds on top of the TensorFlow, which uses TensorFlow. So think of it like Keras as the brain, and then TensorFlow is like the nervous system of the whole body. For TensorFlow, it operates off the CPU or the GPU. But for GPU, it requires the GTX 1060, I believe, or higher, only because it has the CUDA cores and it's built into those graphic cards. I didn't have that, so I trained our model on the CPU instead. For hardware, we just bought a drone. We didn't have time to build one or build a drone or anything like that, so we bought a drone, and we're using the drone as the footage where you can fly up the beam and capture video and send it back to the base computer of where all the processing happens. We tried to use a Raspberry Pi or a small microchip that can connect to the drone, but TensorFlow and the object detection stuff, it's a little bit too intensive for something that small, so we had to just run the program on our laptop or computer instead of something that small. For the screen capture, only because we bought the drone and the DJI drone comes with the app itself, it doesn't allow us to mess with the coding or operate or send the video from the drone itself, so we actually had to use the app. To go around that, we mirrored the phone on which the app is used, only because we can't use the app on the computer. It's only on the phone, because that's how you control the drone. So we mirrored the app from the phone to the computer, and on the computer, our AI is running a screen capture code as well, where it will capture the mirrored part of the phone, which will process through the AI. The thing is, for screen capture, it captures in GRA color format, which is the red, green, blue, and alpha colors, which is usually used in Python or the MSS format. But the TensorFlow and the Keras image library has to be in RGB format. So for the screen capture, we also had to convert the colors from one format to the other for it to work in the AI. We also built a QR code scanner because roller coasters have tens of thousands of bolts, and running a video through the roller coaster, you won't be able to tell where the bolt is or which beam it's on or anything like that. So Disney asked us to create a QR code scanner or a barcode scanner. Our AI can do both, but we have QR code with us right now. It's just a QR code that if they choose, they can put one QR code next to each bolt to identify which bolt it is on the roller coaster, or they can put one at the very bottom of a beam, and they'll just run through like the QR code first. If it detects a faulty bolt, it will return the most recent QR code, and that's where they can check instead of going through like the whole video and going through the whole real time and looking at which specific bolt is the faulty bolt. For training the AI, it takes about, we did it on the CPU, so it takes about 70 to 80 seconds per iterations, and each iteration gets better as you train it more and more. We got up to about 5,000 iterations, and that took about 2-3 weeks of training, constant training. So you kind of just have to like leave your computer on like for weeks on end, and that seems really painful. And after 5,000 iterations, we reached about a 1.9% average loss, which is about 2% of everything that it detects. 2% of the time it will make a little error, and maybe it will detect a bolt or a stripe somewhere where there isn't a bolt or stripe. And IOU stands for interception over union, which is next one. It's to show like where the object is and how far away the detection is located. So if an object is in one spot and then the AI puts the detection over another spot, 80% of it would be inside overlapping the object and the detected box. We tried to get that as close to 100% as possible, but that only takes more time and more iterations. We only got to 5,000, which is 80%, and Disney seemed okay with that one. So this is a quick little flow chart of what our code does. When you start it, it initializes all the libraries and all the configurations if you're running on the CPU or GPU. Running on the GPU is definitely faster. It cuts the time in about half, and for every GPU you add onto that, it cuts more and more in half. So if you really wanted to train more than 5,000 iterations or just as high as you want to get the results that you want, you kind of just add more GPU or just more time overall. So it initializes everything at the beginning. It starts the library, it starts the configurations and the Keras learning and all the models. And if you decided to like stop your training for a quick minute and then pick it up like a different time, you can start from where it left off. And the code will continue just run until it detects a bolt. If it detects a bolt, it will output the confidence levels, and same thing with the stripes. For QR codes, it will process the QR code. It'll compare it to the most recent QR code. If it's the same, it'll just skip over it. If it's different, it'll output where the drone is currently looking at or which beam is looking at.
So basically our AI can identify bolts and torque stripes. It also can acquire video feeds in real time and also video processing. In this case, we're going to demonstrate like using a real-time processing. The AI can also scan QR codes, have a box overlay, indicate quality condition of stripe at a percentage. We're going to demonstrate that right now.
It's not actually demo right now, just to show the different iterations and what results you can get if you just train the model in a longer period of time than what we had. So that 100 iterations, I think we received about 400% loss. It's just garbage. It just detects everything. 500 iterations, it scans the QR code. It still picks up that. And then for the bolts, it doesn't really pick up the bolts yet. I think at about 500 iterations of about 100% loss. for 1,000, it still picks up the QR code, prints it out, and I think it should pick up the volt sometimes. I think with 1,000 iterations, about 80% loss. Two 2,000 iterations was about 40 or 30% loss, I think. So it picks up the volts a lot better. You can still see it, but it's still a little bit faulty. And then our final one where we got to 5,000 is 1.9% loss, and it should pick it up pretty well. So it doesn't like disappear as much, and it will still stay constant on the video. I'm just gonna show like it in real time with the drawings right now.
So what we're doing here, we're mirroring the image from the drone. You can see there using this camera of the Spark DJI, and we're gonna run our application right now. You're gonna see here, that's the application, that's the photos that it's taking. You're gonna see the results right here. That's detecting and showing that in section B12, the bolts 1 and 2 are need to be checked. That's the location, the QR code that we're using to demonstrate the location. And for the bolt, now it's taking this drive with accuracy of 40% or so, and also the bolt. And you're gonna see the output right there on the screen, saying that's a questionable bolt when you need to go and scan it and check it, because we don't have that 100% accuracy if it is a good bolt. We also have a video showing that we recorded with the drone outside, where you can see like the ideal conditions. So that's the video that we took outside. You're gonna see in real time, not right now, but it's detecting while we are recording the video, the stripe and the accuracy of the stripe, if it's good or bad. And we also can record a video and just send it as an input, and it works the same, but it will be a little slower because we're just gonna be using the CPU, and we'll be doing that frame by frame. So for the improvements, as shown in the video, and as Corey said, we need more iterations to give better results. That would mean like we need more pictures to train our model, and also leave it beyond the 5,000 iterations. We also need to keep in mind that it's 3 weeks, and if you guys want to try it, you need to have like a good amount of time to leave your computer running. And the recommended average percentage of loss should be below 1%. Okay. So as I mentioned, we're using the DJI app to mirror the image from to see what the drone is seeing using the camera. And that's a tedious process because we need to mirror that to the computer, and then we use the screen capture feature of our software to analyze it. And it only works on Android phones. And also, it's not necessary to be a DJI. You can be, if we would have had enough time, we could have built our own drone and send the image using that. It's not necessary to be a DJI. And as Corey stated before, TensorFlow has like two different versions, the CPU and the GPU. And to have a better trained model, it would be recommended that to use a GPU and go beyond the 5,000 iterations. And also have high quality images to train the model. TensorFlow is only supporting NVIDIA graphics card right now, and those should be, I think it's from the 1060, GTX 1060 and beyond.
So going on to scheduling and budget. First we started off, so Disney was really insistent when it comes to scheduling. They really want us to make a Gantt chart. So that's what we did. So we made a Gantt chart. That way we were able to list what needed to be done. So you know, like first you do the bolt, then you do the torque strike, then you gotta do the processing and everything. So, but some steps were like making us like a little bit fall behind. So that's when we started splitting it up. And then so for deadlines, we kind of, as we got to second semester, we had to present like at random times. Like sometimes we got to present to students, sometimes we got to present to the freshmen, sometimes we got to do the showcase and everything. So every like presentation, we made sure that we had to have something new, or that our AI was much more accurate. So that showed significant process between each one. So as for what we did individually, Corey worked specifically with TensorFlow CPU. We both originally used JavaScript, but then we made the switch to Python to combine codes because Ricardo did TensorFlow GPU, and he worked on Python the whole time. So I did the QR scanner for both languages. First I made the JavaScript, then I had to move on to Python. So then I did the Python. And then I usually kept in constant contact when it came to Disney or with the school to get everyone updated on everything. And then for the budget, we only had $600 and we just bought the drone. So, thank you.
Questions for the team while the next team sets up?
What's the range of the detecting the bolt? Like you know how you guys show us in live demo, which is about this much, but
It's about 3 or 4 feet.
What's the range of it?
3 or 4 feet.
3 to 4 feet.
Yes, they don't have to be like really up close to it, but not too far away where it's like a little dot.